Welcome to the Podkey summary of Profile, Fix, and Verify. Improve app responsiveness with instruments from WWDC 2026. A lot of this episode comes down to one very practical lesson. The first tool that seems to explain a slowdown is not always telling the whole story. The big themes here are how to read instruments more accurately, how a swift runtime detail can quietly eat CPU, and how to catch main thread hangs that barely show up in the profiler you probably reached for first. There's also a nice thread running through all of it, which is that better labeling and better comparisons can turn performance work from vague guesswork into something much more concrete. Time Profiler is great, but it only records active CPU cycles. So if your app is hanging because the main thread is blocked on I/O or waiting on a lock, the CPU can look mostly idle, and Time Profiler may basically shrug and tell you there's not much happening. That's the trap. If the app feels frozen, but the profiler doesn't show meaningful work on the main thread, that doesn't mean nothing's wrong. It usually means you need to switch tools and look at something like System Trace. In the Save Note hang, System Trace made the problem obvious in a way Time Profiler couldn't. The main thread was spending most of its time blocked, and there was a long write system call sitting right in the middle of it. The trace split that write into on-core time, shown as opaque, and off-core waiting time, shown as translucent, which is a very handy visual distinction once you know what you're looking at. Then the inspector filled in the part that really matters. The app was trying to flush 1.7 gigabytes of data synchronously on the main thread. That led to roughly 300 milliseconds of off-core waiting, which is more than enough for a UI freeze people can feel immediately. And honestly, writing that much data on the main thread is the kind of thing that sounds bad even before you open a trace. One of the most useful habits in this workflow is adding OS_signpost intervals with OS signposter around the code you actually care about. Those intervals show up as points of interest tracks, so instead of hunting through a giant timeline, you can filter the trace down to the exact moment tied to a user action like lasso selection or file writing. They also give you a stable reference point for later comparisons, which matters a lot when you're trying to answer a simple question like, did this change actually help? On the CPU side, the flame graph is still a really good first view because it aggregates sampled call stacks into wide blocks and makes the expensive code paths easy to spot. But hierarchy is also its weakness. If the same runtime helper shows up under lots of different call paths, the flame graph splits that cost across branches, so the total weight of that function can get visually diluted. That's where the newer top functions view becomes a much cleaner lens. It throws away the call tree hierarchy, merges every instance of a function together, and ranks functions by self-weight. So instead of asking where a function appeared, you can ask how much total cost this function is responsible for. Full stop. Using that top functions mode, one runtime function jumped right to the top during lasso selection. Swift_project_boxes_opaque_existential. That function is part of the machinery for unwrapping protocol existential values, which is a very technical way of saying the runtime had to do extra work because the compiler didn't have enough concrete type information up front. And once that became visible, the fix was pretty straightforward. Replacing those existentials with concrete types or generics gave the compiler more static information, removed that unwrapping overhead, and cut CPU time dramatically. It's a nice reminder that a design choice that feels elegant at the source level can carry a real runtime bill. After a change like that, run comparisons helps answer the only question that counts. What changed in the trace? Exactly. It cross-references every sample from a baseline run with an optimized run, matches functions by name, and computes the performance delta directly. The interface marks regressions in red and improvements in green, which is simple but incredibly effective when you're scanning for what got better or worse. It can also highlight new functions introduced by a coding assistant, which is useful because generated changes have a habit of being helpful right up until they aren't. So instead of relying on vibes, you get a measurable before and after. Another performance issue here had less to do with raw CPU and more to do with where work was scheduled. The Swift Executor's instrument lays out the main actor, the global concurrent executor, and any custom executors, so you can see task flow instead of inferring it from a stack trace. That view showed thumbnail rendering tasks queued on the main actor, which meant they were competing directly with UI work. So even if the app wasn't technically doing something outrageous, it was doing the wrong work in the wrong place, and the UI paid for it. Adding the @concurrent attribute to the task initializer moved that thumbnail work onto the global executor, which freed up the main actor and let interaction stay smooth. One more practical point, and it's a big one. Profile release builds, not debug builds. Debug builds keep extra checks around and miss the optimizations that shape real runtime behavior, so they can inflate CPU usage and point you toward hot paths that won't matter in production. The safer workflow is launching instruments from Xcode through product to profile. So you generate a release binary and collect data that actually reflects the app people run. The common theme in all of this is that performance work gets much easier when you stop asking one instrument to answer every question. Use the profiler for active work, system trace for blocking, executors for scheduling, and signposts to keep the whole story lined up. And if one tiny runtime helper suddenly becomes your top function, that's usually your app politely asking for fewer abstractions at 60 frames per second. This episode was generated by Podkey. Create your own at podkey.fm.